So we're essentially going to be looking at, we have parameters and we have statistics. And the idea is a parameter is something we don't know, and a statistic is something we do know. And a statistic is like, we kind of talked about like, hey, the percent of this entire bin that is red is the parameter, which is something we don't know and don't really want to find out because it sounds pretty terrible to try to count them all up, and it would be, right? So then we would do, we might use the percent of this sample that is red instead. And the percent of this sample is the statistic. The percent of the whole bin is the parameter. Everybody good? Okay. Now, some other things I want to point out before we get too much further is I totally screwed this up. Like, totally. This one's mu, this one's x bar. This one's sigma, this one's s. I don't know how I got them backwards because I'm better than that, but, you know, sometimes everybody has an off day. Is everybody, are we good? Typically, the Greek letters are the parameter. Okay. Now, you guys, are you with me that the percent of that bin that is red is always the same number? Of the entire bin. The percent of the population that was red would always be the same number. So something that's also worth noting is that a parameter is constant. It doesn't change. If I were to say there's a percentage of Grandview Heights High School students who left school for lunch today, there is a singular percentage to describe all of the Grandview Heights kids who left for lunch, right? It won't change for today, right? But I could take different samples, like if we did the percent of you guys versus the percent of Richard's class versus the percent of study hall versus the percent, you guys get what I'm saying? Okay? Statistics are variables in that they change because we could get a different value each time, depending on the sample we collect. All right, so one thing we might want to start getting pretty, oh no. I didn't think we were doing the Starburst until Wednesday. I don't have them. We're going to do them on Wednesday. Can we get around this? Monday, okay? Or on Wednesday. We'll get around this. I'll bring the Starburst, okay? All right. Because I was going to go to the grocery tomorrow and get them. All right. In this, all right, so let's go ahead and look at this one again. As we read this, what I want us to do is maybe identify what is our sample, what is our population, what is our statistic, what is our parameter. Thoughts? The population is all U.S. adults.
Is it the population? Sorry.
Nope, it's all good. You don't have to apologize for me writing it in the wrong spot. Okay?
Sample of 550 US dollars.
Okay? What's our statistic? Well, The statistic would be the measurement we take of that sample, yeah?
60 out of 515.
The statistic is, in fact, a p-hat, a proportion from our sample, which is calculated by doing 160 out of 515. Which was what, 30, I just looked and now I don't remember, was it 0.31, 31%? And what are we trying to estimate there? The proportion of all U.S. adults who believe in ghosts. Okay. What about this next one?
Sample would be 318 teenagers.
And what did we measure about our 318 teenagers? That their X bar is 4.5 hours. And who are those 318 trying to represent? All teens. And what are we trying to estimate? The mean screen time of all teens. Okay, so you guys, we are going to do this activity about the starbursts, okay, on Wednesday, but let me explain what that activity will look like, okay? I'm going to have a big bag of starbursts, and I'm going to give each of you a sample of 5 starbursts. Everybody with me? All right, and so, and of course, since obviously I won't even listen to an argument, pink is the best flavor of Starburst, no question. For sure. For sure. We're going to look at what percent of our sample was pink. Cool? All right. So, what would the P and the P hat be in that context? P would be the proportion of the whole bag that is pink. And P hat would be the proportion of the samples. So you guys each would have your own. Now, as we talk about this a little bit more, the proportion of the bag that is pink, is that a constant or a variable? If I have this, the whole bag, it's a constant because a parameter is a constant. What about the proportion of the samples that are pink? They're definitely a variable, right? Because some of you are going to get 2 out of 5. Some of you are going to get 1 out of 5. I've seen someone get 4 out of 5. And then the other one was a red. It was a really good sample. I was really happy for them. Okay? But you guys catch my drift here, right? So which one has a distribution? The P or the P hat?
P hat.
P hat, because it has variability. Okay? Right? And if we did the mean weight of our sample instead, X bar would equal the mean of the sample. And mu would be the mean of the whole bag. And again, mu, constant. X bar, variable. How are we feeling so far? We're on this. All right. All right. So let's go ahead and say Mr. Belk and Mr. Stork each take different samples where they measured how long juniors or sophomores and juniors studied for the ACT. And the average for one sample was 3.2. The average for another sample was 2.6. Why didn't they get the same?
They have different samples.
And what do we know about samples?
Samples are not perfect.
Samples are not perfect. Yeah?
Did you like buy a buzzer that said that, or were you like
That's my voice.
record?
It's one of those dog training buzzers where you can train your dog to press it. And I did not purchase it. It was given to me by my sister. And I thought that this would be a way more fun use of it, given that my dogs are not going to actually hit the button anyway. I know them well enough to know that they're stubborn. Well, one is stubborn, one is dumb. But he's pretty. But he dumb. Okay. All right. And this whole idea is that samples are variables, right? Statistics are variables. And sampling variability happens because samples flat out just won't be perfect. And that doesn't mean we did anything wrong. A sample is not perfectly representative of our population. If we've done everything we can, right? We take a random sample, we use the random digit generator, we do, like we talk about, that sampling process that we kind of talked about earlier in the year, okay? It means our sample is going to be close, right? When we do statistics, we do statistics assuming our sample is representative of the population. But even if it's representative, for example, thinking through this, definitely looks pretty darn close to the makeup of the bin, but it's not perfectly accurate to the makeup of the bin. Is this making sense? Okay, so now, is it possible that we could take every single sample of 10 and measure and find the mean study time for the PSAT? Not practically, but could we do it?
Yeah.
And if we did, all of a sudden, like, here's Mr. Stork's sample, here's Mr. Belk's sample, I could take a sample, maybe it's up here, right? If we take every single possible sample, all of the sudden, we have a dot plot, right? Like, you can think of each of those X bars as a dot on a dot plot, right? Okay? All of a sudden, we have a distribution, and this is a very specific distribution called, in this case, this would be the sampling distribution of X bar. So we call it a sampling distribution when it is the result of taking lots and lots and lots and lots of samples, right? It's the result of sampling, okay? And likewise, there's sampling distributions of p hat. And you can do a sampling distribution of a lot of different things. We're going to focus for right now on two sampling distributions, x bar and p hat. Okay? All right. Now, if you guys, what I'd like you guys to do next is if you go into Schoology, I think it would work on your phones. It probably would be a little bit more user-friendly on laptops, but it would work on your phones. And it's in the Notes tab on Schoology. So go to you would want to go to Unit 5 on Schoology, and then Notes. And there should be a link in the Notes tab that says Art of Stat. Okay, everybody good? All right, and go ahead and let's start with taking this slider down to a 20. Because what we're going to do is look at what happens to that sampling distribution when I have a sample size of 20. So everybody go ahead and draw a sample by hitting the blue Draw Sample button. So mine doesn't look as great as yours because you can't see it as well. Everybody good? All right. And when you look at, like, for instance, in my particular sample that I drew, we had 72.5% of my sample was a yes to whatever our question was. Did any of you guys also get exactly 72.5? No, we all got a different one because we all drew a different sample. That's what this software kind of mimics. Everybody good so far? Okay, now, a sampling distribution is what we get if we do this lots of times. So I'm going to go ahead and draw another sample. And notice that what happened is another case got added onto my graph. So up here is the graph of the singular sample. How many yeses, how many nos? Okay? And down here, it just keeps track of how many samples I have. Is this kind of making some sense? So there's like a p hat right here, and there's a p hat right here, a p hat right here. Does this make sense? So every time I draw a new sample, again, I'm going to draw one more. And you can see this one was a much lower percentage. Is this okay? So lots of p hats. Okay. But a sampling distribution is if I've taken every possible sample. We're not going to take every possible sample. We're going to just stop taking them one at a time. Everybody good? Okay, so I'm going to go ahead and change my number of samples to 10,000. And now we're almost starting to, we can kind of see this is a sampling distribution of p hat. Because it's lots and lots of p hats. Everybody good? All right, now here's what I need us to do. You guys describe to me when n was equal to 20, what was the shape of the graph? Let's see, does this have? If you click on the show normal approximation, yeah, I'm going to go with pretty close to normal. Everybody good? So at n equals 20, we were approximately normal. Okay, and the other thing I want us to know is what is the standard deviation of that distribution of p hats? Okay, I think it tells you on the graph. Maybe. You guys see how it tells us that the standard deviation is 0.103. Okay. All right. So my goal is to show you guys what happens as we increase our sample size, what happens to this distribution of p hats. Okay, there's two major things that start to happen. So let's look at n equals 40. What that means is I'm going to take my this and move it up to 40. Move the sample size slider. And notice it deleted. Oh, it also redid it. And it re-randomized everything. Talk to me about the normality now. Are you guys cool with it's more normal? And what I can see is that, like the last one, a bunch on the right-hand side were like peeking out of the normal curve, but very few over here, and now it's starting to get more balanced. Does this make sense? Okay. And what about my standard deviation? It's smaller. Okay. So we're gonna say more normal. And now my standard deviation of my p hats was 0.07 something. Give or take, it was 0.07. Okay, one more time, guys. What happens at n equals 100? We feeling better? Like what's going on? Even more normal, right? It's this now it looks like that normal curve is almost perfectly on it, right? And the standard deviation's 0.046. Okay. All right. Now, here's kind of why that happens. You guys, if I go back to my bin here, because I just think it's helpful to visualize. If I take a sample of, say, instead of doing all of them, I just take a sample of 11. Okay? Are you guys with me that seems pretty spot on? Decent, right? Would it be super crazy to get a really lopsided sample at size 11? Like, could we get one that has very less reds? Very less. I don't know if that's actually a phrase, but you guys get, like, it would be kind of, like, possible And then our p hat for red would be much smaller than normal. But if I take a sample size of all of them, now it's a lot less likely to get a lopsided sample. Does that make sense? Okay. So what happens is as we increase our sample size, we're less likely to get kind of that wacky, unpredictable sample that just sometimes happens. Did you guys see what I'm saying there? And so what happens, and that works in both really big and really small. So what happens is as n increases, as our sample size for each sample that we draw increases, the statistic, whether it be a p hat or an x bar, the statistic becomes less spread out. Because remember, that statistic is the variable, it's what changes. And the shape of the statistics get closer to zero, or closer to normal. And both of these have some really important and key benefits in terms of the act of doing statistics. If a statistic is super close to normal, what that means is it's more predictable, and easier to do calculations. And here's what I mean by that. We have normal CDF. We have inverse norm. We can do a lot more with a normal graph than a not normal graph. Okay? Now, why would it be important that our statistic becomes less spread out? More consistency in the statistics. I want to bring up, we've got some graphs that we created that are kind of hanging around the room, right? Which one had this? By the way, are you guys with me that these were in fact distributions of x bar? These were a simulated sampling distribution because we just found the mean, right? And which one made it easiest for us to guess the true mean enjoyment? This one. Why? When they're really close together, we know we're close. Yeah, like you know your statistic will be closer to that actual value if it's less spread out. You guys get what I'm saying? Okay? So if it becomes less spread out, that means in general the statistic is closer. Statistics are, because they're multiple, closer to the parameter. And that's really lovely because we're trying to figure out what the parameter is. Eventually, we're going to get to using these to estimate about a population. We want to be close. The closer our sample is to the actual population, the better. Everybody good? Okay, so we got one. We're going to get a thing to talk about. Now, a statistic is considered unbiased if the mean of the statistic equals the parameter. going to go back to this graph again, because since this was a distribution of x bars, and you guys, remember this was the enjoyment rating for the concert, yeah? What's our best estimate at the enjoyment rating of that concert?
78.
Somewhere between 78 and 79. Are you guys all comfortable with that? Good, you should be, because x bars are unbiased estimators. In other words, do we know the mean enjoyment of that concert? No. But we're comfortable saying that the mean of the x bars is equal to the mean of the population. Remember that mu is the population. And it turns out that we're going to spend a lot of time using x bar to estimate mu and p hat to estimate p because they are unbiased estimators. Now, let's talk about the sample range. Who do you think who's the tallest in here? Charlie?
James.
James? How tall are you? 6'3"?
6'3". 6'1".
Okay, so 6'3", tallest. And who's the shortest? I would imagine it's either Kira or me. How tall are you?
5'4".
Okay, it's me. Is anybody taller than 5'2"?
Taller?
You're tall or shorter than 5'2". Anybody shorter than 5'2"? Okay. All right. So you guys, if James is 6'3" and I'm 5'2", what is the range of heights in this classroom?
5'2" to 6'3".
But remember, the statistical range is just the highest minus the lowest. Yes. So you guys with me that the range of our class would be 13 inches. I did that math right?
Mm-hmm.
13 inches. Everybody good? Okay. Now, I'm going to call that capital R. Capital R. $13. Great. Now, we're going to let little r equal our sample range. And let's get a random sample of 2 people. Pick any 2 people you want, you guys. I knew you wouldn't do this. See, it's random. Am I pointing to 2 people?
Yeah.
1. Is this at somebody?
Yeah.
Yeah.
Oh, that's definitely. And then the other one was Dean. Dean, how tall are you?
I'm not sure. 5'6".
Okay.
5'4".
5'4". Okay, so what was the range of that sample, y'all? 2 inches. You with me? Okay. So let's start making a dot plot of these sample ranges. So now, if I take a different sample, I would get a different answer. Okay, so let's go ahead and choose Biscuit and Freya. How tall are you?
6'1".
5'4".
So 9 inches? Is that right? And then I could pick 2 more people, right? Is everybody with me? All right. And let's go ahead and say, could we ever get a sample that had a range of 13 inches if we picked 2 people? We could. Right? It would happen, what? If we were the 2 people, right? And if my sample size was 3 or 4, it would still kind of start to look like this, right? Is everybody with me? Okay. And so, would these be good estimates? Would it make sense for me to take a sample from our group here to estimate the range of all of us? Does that make sense to you guys? Start thinking through, does it make sense to just randomly select 2 of you to estimate that 13 inches?
No, because it has to be lower or equal to every time.
Yeah. Are you guys with me that the mean of all of my sample ranges is less than 13, less than or equal to 13? It's certainly not going to be equal to 13. And in fact, the sample range is almost guaranteed to underestimate the population range. Do you guys see what I'm saying there? Okay, so the range is a biased estimator. It is not a good idea to use the range to estimate the range of a sample to estimate the range of a population.
So then wouldn't it just be less than instead of less than?
Well, technically, we could get a sample that had both of us in it.
Mm-hmm.
Then the range would be 13.
Okay. I thought since it was like the mean, like it was small.
Yeah, it's probably less than. More likely less than for sure. Are we good? All right. Now, the bias that we're currently talking about, in some respects, is not the same thing as the bias we were talking about a few months ago. Okay? Because teaching. Okay. So the bias, this would be an estimator bias, which is not the same thing. I mean, this is a bias that is introduced by picking the wrong thing from our sample. So we could gather a completely appropriate sample and we'd still end up with some estimator bias. And that's not the same thing as, say, non-response bias. So it's not just about how you gather your sample. It's not just about how you gather your data. What you do with that data at the end is another potential source of bias. Okay? And here's something that we really just, I need to I need you guys to get this. Okay? Sample size does not influence bias. It is not a source of bias. Now, if I take that small sample, is it possible that I got that wacky sample? Sure. So sample size can influence how representative our sample is, for sure. But not make a sample, like if I have a bias before I sample, the size of the sample doesn't matter. Does that make sense? If I have non-response bias, taking a larger sample so I have more non-response doesn't do anything. Okay? And why do we want to have less what sample size does is shrinks that sampling variability, which means our samples are closer to our population. I'm going to say that slightly different, are a closer representation to our population. Now I'm done.